Hello everyone, welcome to video number 3 of physics mechanics. In this video, we're first going to learn about Newton's 3 laws of motion, and then we'll start learning about forces. We're going to spend several videos exploring forces because there are a lot of different forces. You've already learned about kinematics, and forces build upon kinematics by letting you know what causes the motion of objects. But without further ado, let's dive into Newton's 3 laws of motion. Before we get into Newton's 3 laws of motion, first you should know what a scientific law is. A scientific law is a statement that has been made due to repeated observations or experiments that support the statement, and no observations or experiments that contradict the statement. So it's possible that someday a scientific law could be disproved if somebody finds an observation or experiment that contradicts the statement, but a statement being a scientific law means that to date, nobody has found any observations or experiments that contradict the statement. So now into Newton's first law of motion, also known as the law of inertia. And it states that an object will not change its motion unless acted on by an unbalanced force. And an unbalanced force means that the force is not canceled out by another force. An example of a place where you can apply this law into your own life is when you're in a car and the car comes to a sudden stop, you continue to move forward because your motion will not change until you are acted upon by an unbalanced force. This is why you wear seatbelts. Seatbelts apply a backward force on you to prevent you from falling forward and potentially hitting the front of the car. To see Newton's first law in action, we're going to explore a PhET simulation, which I'll link down below in the description. We're going to click on acceleration and check values in speed and slide friction to none. So right now, the law of inertia is holding because there are no forces being applied on this box right over here, and its speed is therefore staying at 0 meters per second. Now, if we apply a force on it, say 100 newtons, and then we release, then this box is going to stay at a constant speed, in this case 7.7 meters per second, because there are no forces being applied on it anymore, and it's going to stay like this until we apply a force on it. Now on to Newton's second law of motion. It states that force is equal to mass times acceleration, and the units must be newtons for force, kilograms for mass, and meters per second squared for acceleration. We're going to use the same PhET simulation to see Newton's second law in action. So keep in mind that you can press this button to reset. This time we're going to check values, masses, and acceleration and slide friction to none. And if we apply a force of 50 newtons, you'll see that Newton's second law of motion holds because the mass 50 times the acceleration 1 is equal to the force 50. And if we change the applied force to 100, you'll see that Newton's second law still applies because 50 times 2 is 100. Now, if we apply a force of negative 50 newtons, and negative 50 just means that it's going left this time, then Newton's second law of motion still holds because 50 times negative 1 is equal to negative 50. Now on to Newton's third law of motion. It states that when one object applies a force on another object, the second object applies an equal and opposite reaction force on the first object. Opposite means that the force acts in the opposite direction as the first force. An example of this law in action is in the PhET simulation when the person was pushing on the box with the force of 50 newtons to the right, the box was pushing on the person with a force of 50 newtons to the left. The simulation didn't show this, but it's true. Some more examples are when you jump, you're pushing down onto the ground, and therefore the ground is exerting a force up on you, allowing you to rise into the air. And when you punch a wall, it doesn't hurt because you're applying a force on the wall. It hurts because the wall is applying an equal and opposite reaction force on your hand. Now we're getting into forces. Having learned about Newton's first law of motion, you now know that any and all changes in motion are caused by forces. When you stand up, there's a force. When you start or stop walking, there's a force. When two magnets attract or repel each other, there's a force. There are so many examples of forces. In this video, we're going to be exploring three forces: gravity, normal force, and tension. So let's start with gravity. Gravity is an attraction force that exists between any and every pair of two objects in the universe. So there's gravity between you and the Earth, there's gravity between the Earth and the Sun, there's gravity between you and another object in your room. However, gravity depends on mass, and since the mass of you and another object in your room are both so small, the force of gravity is so small that it is overcome by other forces such as friction, which we're going to explore in the next video. On Earth, the force of gravity on any object is 9.8 times the mass of the object, newtons, and we'll explore why this is true in a future video. And 9.8 should seem familiar. It's the acceleration due to gravity on Earth. Gravity is a non-contact force because it exists between any pair of two objects in the universe. The two objects don't have to be touching. Weight is the force of gravity on an object. So if the force of gravity on an object is 40 newtons, you could say that its weight is 40 newtons. And keep in mind that weight depends on where you're standing. So if you're standing on the moon, then your weight would be lower than the weight if you're standing on Earth, because the force of gravity on the moon is lower than the force of gravity on the Earth. Normal force is exerted on an object that comes into contact with a surface. It's always exerted perpendicular to the surface. That's why it's called normal force. You may have thought that normal means ordinary, but in this context, it means perpendicular. So a common case of normal force is when an object that's pulled down by gravity rests on a surface. So the surface exerts normal force on the object to prevent it from sinking down into the surface. So right now, wherever you're sitting or standing, the surface that you're on is exerting normal force on you to prevent you from sinking down because you're being pulled down by gravity from the Earth. And another common case is when an object collides with a surface with a certain speed. So the surface applies normal force on the object to prevent the object from going into the surface. So for example, if you hit a ball against a wall, then the wall exerts normal force on the ball when they collide to prevent the ball from going into the wall. And normal force is a contact force because the object and the surface have to be touching. Lastly, tension. Tension is applied by a rope that is taut or fully stretched. It is applied in the direction that the rope is stretched. That might be confusing, but soon I'll show you a diagram and you'll see what that means. Tension is applied on both ends of the rope, and on either end, the magnitude of tension is the same. Tension is a contact force because it is only applied on objects that are touching the rope. Now we're getting into free body diagrams. These let you know all the forces acting on an object and approximately how strong those forces are. Free body diagrams show each force acting on an object as vectors. So this is similar to what we saw in the previous video, except instead of velocity vectors, this time we're dealing with force vectors. Let's draw the free body diagram for a box on the ground. Since this is on Earth, there has to be gravity acting downwards, and in order to balance that out so the box doesn't sink into the ground, normal force acts upwards. And in order for the forces to balance out, the magnitude of the normal force must be equal to the magnitude of gravity. Here are some more free body diagrams. For a box hanging off a rope, there's still gravity acting downwards, but this time, tension is the force that balances it out, not normal force. For a box hanging off of two ropes, there's still gravity, and this time there are two tension vectors, each one pointing in the direction of a rope. And the forces still have to balance out since the box is not moving. So if you add the vectors together, they have to add up to 0. So the x components add up to 0, and the y components also add up to 0. So this one's a little more challenging. A person pulls up and to the right on a box using a rope. The box accelerates to the right, but not up. So this time there's still gravity and normal force, and then the person pulls on the box using a rope, so therefore there's tension, and then there's also friction because the box is staying on the ground, which we're going to explore friction more in the next video. So this time the forces do not balance out because the box is accelerating to the right, so therefore the x components, they do not add up to 0, but the y components do add up to 0. And that's why the normal force, the magnitude of the normal force is less than the magnitude of gravity, because if they're the same, then we also have to consider the y component of the tension force, and then the y component of the net force will not be 0. Now we're getting into pulley systems. Pulleys allow you to control the direction of the force of tension, and that could allow you to lift up heavy objects. A pulley system causes a rope to not be completely straight, and that affects the direction of the force of tension. So here's an example of a pulley system, and I'm going to show you the free body diagram for each block. The forces of tension have the same magnitude. So here's an example problem. How fast does the 10-kilogram block accelerate downwards? To solve this, you would use Newton's second law, F equals ma. So first, you need to determine the net downward force acting on the 10-kilogram block. It's downwards because the block is accelerating downwards. So the net force is the force of gravity minus the force of tension. And the force of gravity, you know, that's 9.8 times 10. And then the net force is just equal to the mass, which is 10 times the acceleration. And now the net upward force acting on the 5-kilogram block, and it's upward because the 5-kilogram block is accelerating upward since it's not as heavy as the 10-kilogram block. So that is force of tension minus force of gravity. And the force of tension is the same as the one above, but this time the force of gravity is 9.8 times 5. So the net force this time is equal to 5 times A. So now we have a system of two equations, and if we solve this, we're going to get A. A is equal to 3.27 meters per second squared. So this is one method you could use to solve these problems. A faster method is just to find the acceleration with regards to the overall system instead of each block. So you first find the net force acting on the entire system without considering the tension of the forces of the ropes in the system. And then you divide by the total mass of the objects, and because that's the total mass of the system. And then you have the acceleration of the system. So let's use this method on the example problem. So the net force acting on the system is 9.8 times 10 minus 9.8 times 5. We subtract 9.8 times 5 because the 5-kilogram block is on the other side of the pulley. So that is equal to 49 newtons. And then the total mass of the objects is 10 plus 5, which is 15. So the acceleration of the system is 49 divided by 15, which is 3.27 meters per second squared. So we get the same answer. You can use the faster method to solve more complicated systems. So for this system, if you're going to use the first method, then you would have a lot of different ropes and each one has its own force of tension. So in your system of equations, there will be a lot of variables and that will take a long time to solve. However, to solve this using the second method, we first find the net force acting on the system. So we add up the forces of gravity acting on the blocks on the right side, since the right side's heavier. So we get 9.8 times 10 plus 9.8 times 10 plus 9.8 times 5. And then we subtract the forces of gravity acting on the blocks on the left side. And the net force acting on the system is 49 newtons. And then we add up the masses of all of the objects, which is 45 kilograms. So the acceleration of the system is 49 divided by 45, which is 1.09 meters per second squared. So now here's another system. If you want to try to solve this by yourself, pause the video here. You can use either method. The solution will come in 3, 2, 1. So if you're using the first method, you first determine the net rightward force acting on the 8 kilogram block. That is 100 minus the force of tension of the rope, and that is equal to 8 times the acceleration. And then the net rightward force acting on the 2 kilogram block is just the force of tension of the rope. So that is equal to 2 times A. And if you solve this system of equations, you'll get A is equal to 10 meters per second squared. And using the second method, you first determine the net force acting on the system. That's just 100 newtons. And then you add up the masses of the objects to get 10 kilograms. So the acceleration of the system is 100 divided by 10, which is 10 meters per second squared. So here's another system. If you want to try to solve this by yourself, pause the video here. The solution will come in 3, 2, 1. So using the first method, you first determine the net downward force acting on the 8 kilogram block because that's the direction it's accelerating in. It's force of gravity minus force of tension. You know the force of gravity is 9.8 times 8, which is 78.4. So the net force is equal to 8 times A. The net rightward force acting on the 2 kilogram block is force of tension minus 10, and that is equal to 2 times A. So solving the system of equations gives A is equal to 6.84 meters per second squared. Using the second method, you first find the net force acting on the system. That is the force of gravity acting on the 8 kilogram block minus 10. And it's minus because the 10 newtons is going against the direction that the 2 kilogram block is accelerating in. So then the total mass of the objects is 10. And dividing 68.4 by 10 gives 6.84 meters per second squared. The final topic is Newton's third law pairs. Remember that Newton's third law states that for every force, there is an equal and opposite reaction force applied on the object that applied the action force. The force and its reaction force are called Newton's third law pairs. Now you might be wondering, are gravity and normal force Newton's third law pairs? And keep in mind that we're assuming the situation is an object resting on the ground on Earth. So this is logical to think because normal force is equal to and opposite to gravity. However, the answer to the question is no, because the reaction force must be applied on the object that applies the action force. And since gravity and normal force act on the same object, they cannot be Newton's third law pairs. So gravity in this situation is the Earth pulling on an object. So therefore, the reaction force has to be the object pulling on Earth. And these two forces are equal in magnitude. Now you might be wondering, if they're equal in magnitude, then why doesn't the Earth fall into the object? Well, remember that force is not what directly tells us about the motion of an object. Acceleration does. The mass of Earth is approximately 5.97 times 10 to the 24th kilograms. And since force is equal to mass times acceleration, the acceleration of Earth is so small that it is effectively zero. So that's why we don't see the Earth fall into the object. Now you might be wondering, what is the third law pair involving normal force? Normal force is a reaction force. The action force is an object pushing down on the ground, and normal force is the ground pushing up on the object. So these two forces are third law pairs. So a quick recap of today's topics. We started with Newton's 3 laws of motion, then learned about gravity, normal force, and tension, and then we learned about free body diagrams, Pulley systems, and Newton's third law pairs. Thanks for watching. I'll see you in video number 4.